In this video, I'm going to explain to you how to simplify radicals. When we talk about radicals, we mean the square root symbol, as you'd probably think of it, which we know as the radical. And the numbers under the square root symbol, or the algebraic expressions, let's say a times b, is known as the radicand. Okay, so you should know those two definitions. They might come up in your textbook, or your teacher might use them in class. And the radical is a way of kind of doing the opposite of exponents. So with exponents, we say 3 to the second power is equal to 3 times 3, or the repeated multiplication of 3, and that equals 9. If I wanted to show what the opposite of the radical is, well, the square root of 9 is the number which when we multiplies by itself to get 9, that's 3. Radicals can express different roots. So I could say the fourth root of 16 is 2. And that's because 2 to the fourth equals 16. One thing you need to know is that the radical always expresses a positive value. So this is sometimes known as the principal square root, but I'm going to just call it the positive root. And the reason you should know that is for solving some equations, you'll see that we can solve an equation like x squared equals 9. This equation says what number squared equals 9. When solving an equation like this, we usually think of taking the square root of both sides, but really what we're doing is we're finding the positive and negative square roots of 9 to express both square roots. And so the answers to an equation like that are plus or minus 3. Outside of solving equations, sometimes we have expressions such as the square root of 9. This is not plus or minus 3, but rather, since there's no plus or minus before the radical, this is just positive 3. There's only one value to the square root. It's important that you understand that the radical sign, when it's used for square roots, always means the positive square root. Okay, well, let's start talking about how we simplify square roots. Here I've listed a number of square roots that are the square roots of perfect squares, such as 9, 7, and 18. Each of these numbers, when I square them, gives me the number under the radical. So we think of 9, 49, 324, and other perfect squares as having square roots that are rational, or that are going to be nice, easy numbers to think about. But what would the square root of a number that's not a perfect square be? For example, 2. What number times itself would be equal to 2? Well, I could try multiplying some things like 1.5 times 1.5. And that's a little more than 2, so maybe 1.4 times 1.4. See if that works. That's a little less than 2, so maybe 1.41. I'll just square it, that's a little faster. Getting closer. What about 1.42 squared? That's a little more than 2, so it's got to be in between those. Maybe 1.415. A little too much. 1.411. Too little. So 1.412. We'll try that. Getting closer. 1.413 maybe. Getting closer, 1.414. I could keep doing this for a long time to try and figure out the exact square root. Or I could use the square root button on my calculator to have the calculator estimate it. And you can see that I got pretty close with 1.414. I would have had to keep going. The actual answer is a little more than 1.414. But this decimal, in truth, never ends. So we could go on forever. We'd never get a number that was exactly equal to the square root of 2, that when we multiplied it by itself gave us the square root of 2 if we try to use decimals. So 1.414 is not equal, so I should get rid of the equal sign. It's about equal to the square root of 2. To be precise in math, when we take the square root of a number that's not a perfect square, we end up with what's called an irrational number, and that number is always going to end up being expressed with a radical as part of it. So we'd say the square root of 2 is really the square root of 2 when we try to simplify it. Square roots have some properties that we use to simplify, and so you should know two properties. The first property that I'm going to explain is called the product property, and it says that the square root of a composite number, like a times b, is equal to the square root of a times the square root of b. I want to give you an example to try to help this make sense. I'm going to say that the square root of 4, let's call that a 4, times the square root of 4 is equal to the square root of 16. When we multiply square roots, we just multiply the radicands together. Well, if this is true, well, the square root of 4 is 2 times the square root of 4 is 2, and the square root of 16 is 4, then 2 times 2 must be equal to 4, and it is. So this property is often used in helping us simplify square roots. The way we use this property is kind of the opposite of that example I just gave. We can take square roots like the square root of 12 and start to break them apart into their factors. So I know 12 is like 4 times 3. So the square root of 12 is equal to the square root of 4 times the square root of 3. And I know the square root of 4 is 2, so I could write 2 times the square root of 3. This is the simplest form of the radical square root of 12 because the radicand in this expression has no perfect square factors. No perfect square factors. That's what I'm trying to remove when I simplify these square roots. Let's do another one. The square root of 20. I can break that up into 2 times the square root of 10. So square root of 2 times the square root of 10. And 10 can be broken up a little bit more. 10 is the square root of 2 times the square root of 5. Well, let's think. If I multiply the square root of 2 times the square root of 2 times the square root of 5, when I multiply the square root of 2 times 2, I'll just get 2. So that means that the square root of 20 is equal to just 2 times the square root of 5. Because 5 has no factors that are perfect squares, and there are no numbers that I can split it up by, then that's the simplest form of the square root of 20. Let's do another example. What if we tried to take the square root of 50? Well, I know I can break 50 up into 5 times 10, and 10 is 2 times 5. And again, I have a pair of the square roots of 5. So if I multiply these all together, the square root of 5 times the square root of 5 is just 5 times the square root of 2. You'll notice I did these out of order, but I could have just as easily rewritten this expression to be the square root of 2 times the square root of 5 times the square root of 5 and kept them together. So don't worry about the order in which the square roots come in. We're just trying to multiply them across to find any pairs that we can link up. Now I'm going to try to find the square root of 48 and simplify it. I know that 48 is 6 times 8, and I know that 6 is 2 times 3, and 8 is 2 times 4. 4 is really just 2 times 2. So I think when I factor 48, I get 2, 3, 2, 2, 2. And I'm going to just check really quick. 2 times 3 is 6, times 2 is 12, times 2 is 24, times 2 is 48. And I have some pairs of 2's. There's a pair here, so that will be equal to 2. And there's a pair here, so that will be equal to 2. So I'm multiplying all of these, so I have 2 times 2. And then there's no pairs that go with the 3. So the simplest form of the square root of 48 is just 4 root 3. Let's do one more. I'm going to try the square root of, let's do 300. Well, to start out, I know that the square root of 300 is equal to, just kidding, let's not do 300. You can do 300 as an exercise for yourself. I think it works the same as the other ones. I wanted to show you one different thing that can happen. Let's do the square root of 60. The square root of 60, I can break 60 up into 6 times 10. And I can break 6 up into 2 times 3, and 10 is 2 times 5. And I get a pair of 2's when I simplify. So those 2's make 2. But there's nothing to pair with the 3 and the 5. So when I write the simplest form, I don't write it like this, 2 root 3 root 5. But rather, I write it as 2, and I recombine these to make the square root of 3 times the square root of 5 is equal to the square root of 15. So 2 root 15 is the simplest form of the square root of 60. Okay, so far I've showed you how to use the product property to simplify square roots. In the next video, I'll work on some more advanced examples and how we simplify other kinds of square roots.